Let us now discuss the first type of AGC, which is called simple AGC. Just now we have defined the purpose of AGC. In or automatic gain control, we should somehow be able to read the incoming signal amplitude level, and if it is very large, then we have to reduce the gain of the receiver. If the incoming signal amplitude level is very small, that means if the incoming signal is very weak, then we should allow receiver to operate at its maximum gain value. So that means we have to adjust the gain as per the incoming signal amplitude level. So in terms of a graph, let's say if I plot on the x-axis incoming signal strength, and on y-axis if I plot the gain, on y-axis if I plot receiver output voltage, then when there is no AGC, as the incoming signal strength increases, output signal voltage will also keep on increasing. So this is a curve which represents no AGC. Now whenever there is simple AGC present, in simple AGC what should happen is, as the incoming signal strength increases, the gain of the receiver will start decreasing, and hence the output of the receiver will also start decreasing. So decreased output will look something like this. So as you can see, the incoming signal strength increases, the receiver output voltage also decreases, and as can be seen in the later part where most of the signal amplitudes will fall under normal conditions, the receiver output voltage can be maintained almost constant. If not perfectly constant, it can be maintained almost constant. So this curve represents simple AGC. So the definition of simple AGC is that somehow read the strength or the signal level of the incoming signal and reduce the gain of the receiver if the signal amplitude is increasing. Now let us try to understand how this can be done. We have taken a circuit diagram of simple diode detector to understand how AGC can be implemented. In practice, it will be a practical diode detector that we already discussed. You can see the diode is placed with its cathode pointing towards the input side. That means it is reversed and used in the diode detector. Now whenever such is the case, if I draw the final output waveform, I will get the negative envelope of the modulating signal. So I will obtain negative envelope of the modulating signal, and not just that, this negative envelope will be shifted by some amount which will be the negative DC signal. Now if you remember, we had taken one extra path from the output of this circuit. So we take this path from the output of the circuit and we send this signal through a low pass filter. If I send it through a low pass filter, this RNC will form a low pass filter. The cutoff frequency of this low pass filter will be set in such a way that it will not allow this AF, which is audio frequency, to pass. It will bypass the audio frequency. It will only allow the very small DC frequency to come at the output side. Now DC frequency is frequency equal to 0. That means the cutoff frequency of this low pass filter will be very small. So output of this filter will be almost a constant signal, a DC signal with frequency as small as 0. Now what is the use of this negative DC signal? Why do we need this negative DC signal to be extracted from the incoming signal? Incoming signal which we have on the input of the receiver and then on the input of the detector that we have just now taken, let's say is double sideband full carrier signal. Now every DSB FC signal has got some DC part available in it. It is the value by which the two envelopes have shifted away from each other. It also represents the carrier amplitude. We make sure that the carrier amplitude is very large on the transmitter side. As the signal travels through the channel, this amplitude reduces. So whatever negative DC that we extract is nothing but it also tells us the amount by which the signal is attenuated when it travels through the channel and other systems before it reaches to the detector. So if the incoming signal is very strong, then the negative DC that we extract will also be large. If the incoming signal is very weak, then the negative DC that we extract will be very small. So in simple words, by extracting the negative DC from the demodulated signal, we are able to read the incoming signal amplitude. I repeat, if the incoming signal is very strong, then the negative DC will be large. If the incoming signal is weak, then the negative DC will be small.